This is the first of two videos talking about section 5.2. In this video, I'll be talking about definite integrals. So what is a definite integral? Well, previously we talked about the problem of finding the area bounded by a curve. And so we have an integral notation for this area, which we call a definite integral. So we write the skinny s symbol, which we've seen before, but we're not going to quite yet talk about the connections between this integral and the previous kind of integrals that we talked about. The two numbers, the starting point a and the ending point b, we write on the bottom and top of our integral sign, respectively. So a we call the lower bound, and b we call the upper bound. And then the function that we're actually trying to find the area of, we write that next, and then we write dx. So this function f is sometimes called the integrand. That's not a word I'm going to use too often, but that's a word you might see if you read through the book. So that's our notation for this area problem. So it's nothing new. It's what we've been talking about before. We just have a notation for it now. So we also talked about how we can approximate this area using a Riemann sum. So symbolically, what we're saying is that this definite integral, which is the exact area, is approximately equal to our Riemann sum, which is an approximation of the area. And remember, that was finding areas of rectangles, where this f of x k star, that was the height of my rectangle, and delta x, that was the base of my rectangle. And so I computed base times height, found a bunch of areas, and then added them all together. So it sometimes happens, though, that the actual value that we get when we plug into our function turns out to be negative. So if the function dips below the x-axis, we're going to get regions that are below the x-axis. And so the area of that corresponding rectangle that we get would also be negative. So you can imagine that the xk star that I'm choosing might be, let's say, here on my x-axis. And when I draw my rectangle would go below the x-axis. And multiplying base times that quote-unquote height would give me a negative value. Even though the area of a rectangle can't technically be negative, the actual value that I would be computing would be negative. So those regions that are below the x-axis contribute negatively to that area calculation. So we say that definite integrals measure what we call as net area. So that word net you think of as sort of income minus expenses is your net income, right? So you think all of the money that you bring in minus the money that you spend, that's your net. So that's essentially what we're doing here. We're counting this positive area above the x-axis, but then we're subtracting this negative area that's below the x-axis. And the difference between those two is what we call net area. So as an example, let's approximate this integral using a Riemann sum with 4 subdivisions and using the midpoint of each interval. So this is very similar to a problem that we've done before. The only difference is that I'm using the integral notation to represent the question that I'm asking. So this expression right here, that's still my f of x. Instead of giving you the interval, I'm giving you in terms of an integral. So this -1, that's my a. This 4, that's my b. So I've got all of the information that I need to do the Riemann sums that we were talking about previously. So the first thing I'm going to do is figure out delta x. So delta x is b minus a divided by n, which in this case n is 4. So I get 5 divided by 4, or 1.25. And then I'm going to write my number line. So I'm going from -1 to 4. I've got 4 subintervals, so I'm going to draw 3 dividing lines, 1, 2, 3. So I've got my 4 subintervals there. I'm going to use my delta x to figure out where those dividing lines are. So from -1, if I go up by 1.25, I end up at 0.25. From 0.25, if I go up by 1.25, I end up at 1.5. Add again, I get 2.75. And then just as a double check, if I go up by 1.25 one last time, I end up at 4. And so my xi stars, or my xk stars here, are going to be the midpoints of those subintervals. So in this case, the midpoint is the average of those two numbers, -1 plus 0.25 divided by 2. That's going to be -0.375. Here, my average of 0.25 plus 1.5 divided by 2. That works out to be 0.875. And then the average here, 1.5 plus 2.75 divided by 2. That value is 2.125. And then finally the average here, 2.75 plus 4 divided by 2, again taking the average to find the midpoint, we get 3.375. So those are the values that I'm going to plug into this function. So I'm going to make my chart. So I've got 4 rectangles, so my chart is going to have 4 rows. I'm going to have a base, and I'm going to have a height. My base is going to be 1.25, that was my delta x, so that's the base of each of my rectangles. The height is going to be f of those values in red that I found over here to the left. So the first height is going to be f of negative 0.375. The second height is going to be f of 0.875. Then f of 2.125. And then finally f of 3.375. And I worked these out already. I'm using my calculator here to plug into, again, I'm plugging into this f of x that we have up there. So my first height, just reading these off my calculator, is negative 33.51. Next one is negative 17.98. Next one is 1.84. And last one is 14.24. Next, I'm going to compute my area. Area is base times height. So I'm going to multiply 1.25 times negative 33.51, 1.25 times negative 17.98, and so on. And when I work those out, I get negative 41.89 for the first one. And then I get negative 22.48. I get 2.30, and then I get 17.81. And then finally, I add all these up. And my total area approximation is negative 44.26. So let's think about whether that negative answer actually makes sense for this function. So if I graph this function on the interval from -1 to 4, what I see is that the area that I've been approximating here, remember that's the net area bounded by this function and the x-axis, I've got a big chunk of negative area here, and then I've got a chunk of positive area over here, but the negative area is bigger than the positive area, and so it makes sense here for me to get a net negative area here, because the negative part of my area that I'm approximating is much bigger than the positive part. So in that sense, the approximation that I'm getting seems reasonable. Let's do some more kinds of examples. So this time I'm asking you to evaluate this integral exactly. So how in the world are we going to get an exact answer for an integral when all we've been talking about so far is approximations? Well, let's see if we can figure out a clue by graphing this function. So I'm going to graph y equals negative 2x plus 8. That's a line. It's got slope -2, and it's got y-intercept 8. So the y-intercept is up here at 0, 8. The line has slope -2, so it's going to look something like that. And I'm going up to x equals 6, where I'm going to get the point 6, and if I plug 6 into that, I'm going to get -4. So what we're seeing here is that our graph, our area that we're talking about, has two pieces. As we've seen in the previous example, we've got a positive piece and we've got a negative piece. But those pieces are both triangles. And so we can figure out the areas of those triangles just using the formula for the area of a triangle, namely 1/2 base times height. All we have to do is figure out the bases and the heights of these triangles. Well, the height, that's not going to be too hard. In fact, we've already pretty much figured that out. The distance here is 8 because the y-coordinate of that point is 8. The height here is 4. The distance from the x-axis to that point is 4 units because it goes down to -4. So the thing that we don't know is the bases. What are those horizontal distances? Well, to figure those out, all we need to do is figure out where does this function cross the x-axis? Where is this point where this line crosses the x-axis? Well, the x-axis is where y equals 0. So all I have to do is set -2x plus 8 equal to 0 and solve. -2x equals -8, x equals 4. So this point right here is actually the point 4, 0. Which means that the base of the bigger, the green triangle here, is 4. And then from 4 to 6, the base of this smaller triangle, the negative triangle, that's 2. So now I can figure out my areas. So the area of my positive triangle, that's going to be 1/2 times base, which is 4, times height, which is 8. That's going to be 16. And then the negative triangle, that's going to be 1/2 base, which is 2, times height, which is 4. That's going to be 4. So what's my integral going to equal? Well, it's going to equal the positive area minus the negative area. Remember, it's net area, so it's going to be the positive 16 minus the 4. That's going to work out to be 12. So using a little bit of geometry, a little bit of detective work to figure out the distance here, we can use our basic area formulas to get this exact area. Let's do one more. The integral from negative pi to pi of the sine of x exactly. Well, the sine of x, that's not a line, so we're not going to be able to use triangles or any of the stuff that we did in the previous example here. But again, let's graph this function and see if we can find any clues. Hopefully we know what the sine graph looks like. Something like this. Waving back and forth forever. Here's pi over here, and here's negative pi. And so if I'm integrating from negative pi to pi, again, I see that I've got a negative chunk of area, and I've got a positive chunk of area. And the symmetry of this function shows me that these two shapes are the exact same size. Sine is the graph of y equals sine of x, that's a very symmetric graph, and so those two shapes are exact same size, which means the negative area is the same amount as the positive area. And so those are going to cancel out, and so we get 0. So we don't actually know what the actual areas of those red and green shapes are. Eventually we're going to be able to figure that out, but for now we don't really know how big those shapes are. But what we do know is that whatever the size of those shapes are, they're the same size. And since one's positive and one's negative, they cancel out and we get 0. So for the moment, we can be a little bit clever and use some different techniques to figure out some of these integrals. Eventually, we're going to learn some other tools to be able to solve more of these problems in general.